All right, well, welcome everyone. I am JJ. Let's tackle an example problem. This time we are saying we have the curved bar, goes from A up to B and then over to C, is loaded, 850 newtons out there at C, and support is shown by a pin at A, a cable at B. Let's find our support reactions. So remember, we're drawing free body diagrams. That should be our first step. If we're finding support reactions, I'm using an equilibrium equation. I should have a free body diagram that goes along with that. So I'm going to circle around my object, trying to cut through anything that is holding it up. So I'll start up here, and I'm going to come down and figure out why my pen's not writing. There it goes. If I'm going to come down, and I need to cut through that pin at A. So those will show up as unknowns. And then I can come up and around. I'm trying to just go near the object. To completely free this, though, right now, if I go up and around kind of the wall here, I'd be cutting the wall, which is just a weird thing to do. But it would just be dangling by the cable, even if I didn't cut through that. I gotta cut that cable to fully free the object. And that's what we're shooting to do, is free the object, draw it out. So in my free body diagram, everything inside this circle has to show up in here. Everything we cut through will be an unknown then. So let's come down and draw our free body diagram as our first step, FBD. We should have in here just our curved bar. So we get something kind of like this. I know at the top right corner of that, there's an 850 Newton force coming straight down. 850 Newtons. At A, I have a pin, so I can put in an AY and an AX, and I'm just guessing directions for my unknowns here. AY, I'll guess goes up. AX, I'm going to guess is positive, or is in the positive X direction. AX. I know that from A to where we change the angle on this is given as 300 millimeters. 300 millimeters. From that angle change to the far right edge of this is 275 millimeters. One common thing that shows up as we start drawing this is we don't get everything dimensioned well. Don't stress out about that. This should be bigger. We can all tell it's definitely not bigger. 300 is bigger than 275. Don't stress out about that. I don't care if your drawing is perfect. Odds are your professor doesn't care either. Just get the drawing down there. If we were doing this in a professional setting, we'd be doing this on a computer and it would tear through, getting it perfectly dimensioned out for us. By hand, just get something that loosely looks acceptable. At B, I'm going to have my cable I need to put in here. Cables, we should be able to guess the right direction on this. Cables have to be in tension, so my arrow should leave that circle that I drew. So it's going up and to the left. Is my tension in cable B. Let's call that TB. And I know two angles related to that. I know that from horizontal down right here is 40 degrees. 40 degrees. I also know that from horizontal up to my cable is 22 degrees. So we can label both of those angles. To really do this though, there's one more variable that I need in here. When it comes time to some moments, I'm going to need to know my distance. How tall is this thing? So let's get one more variable labeled in here. From the bottom up to the top, I'm just going to call H. And let's actually start out and find H. I know it's easier to see if we draw this angle in here. My alternate interior angle theorem should tell me if I know that from horizontal down to this slope line is 40 degrees, when I go to the opposite side of that line and still on the inside, from horizontal up to it should also be 40 degrees. If I'm trying to figure out this height, then I can use trig. Tangent is defined as opposite over adjacent. This height right here is H. Adjacent is 300. My angle is 40. Really, I could rearrange that to say that my H height is adjacent 300 tan 40. Or doing the algebra, if we divide by 300, tangent of 40 is H opposite over 300 adjacent. But solving for H, I'm going to get that the height of this is 251.7 millimeters. which is all the dimensions I need to really be able to tackle this. From there, I can come in and start trying to figure out what equilibrium do I want to do first in this one. If I sum forces in the x, that's one of our options. I have ax as an unknown, and I have tb as an unknown. Two unknowns. If we don't have to, let's not start there. In the y, I'd have ay and tb, again, two unknowns. If I can avoid making a system of equations, let's start with one equation, one unknown. It'll make everything go easier for us. So neither force equation is a great one to start with. Is there a moment equation that I could tackle? Would be where I'd want to go with that then. Is there someone that I could eliminate two of my three unknowns? If I sum moments at A, I get rid of AX and AY really easily. I'll have both the X and Y component of TB in there, but it's the same unknown, so I can work with that. So let's sum moments here about point A with positive going counterclockwise, summing my moments up about point A is going to get me, let's start with the, let's do the Y component here first. This is equal to TB's Y component, if I pulled up on this, would cause a counterclockwise rotation. So it'll be positive in here. Fy TB sine 22 times the distance in the X from TB's Y component from my arm over to A is 300 millimeters times 300. And then we can get the X component in. That X component should be going horizontal right here. Pointing to the left, that would cause a counterclockwise rotation down and around A. So we'll add it in as well. Plus TB cosine 22 force times our distance. Well, that should be from the X component down to A is our height, H, 251.7. And then we'll get on the next line. But my 850 will also cause a rotation in here. If I push down here, it's going to cause a clockwise rotation. So subtract it out. Minus 850. That's my force. Times my distance, 300. Plus 275. Or I could just put 575 in there. Really, it's the same thing. But that's everything. That's going to get rotation about A. I can set this equal to 0. Even though it shows up in here twice, TB is my only unknown for that. If you're doing your algebra on this, get rid of these trig identities. Convert those into decimals right away. No one wants to carry through trig identities. This isn't a calculus class, a math class. Round your stuff off. It's going to make your math a lot easier. You'll be more likely to get the right answer. Get rid of those trig identities. Convert them to decimals. And then do the algebra. But I can solve that for TB. I'm going to get that my tension in cable B, TB, is equal to 1,413 newtons, which would be my answer for everything. If it's a cable, I'm probably not going to require my students to put in that direction on it because we all know it has to be in tension just in whatever direction the cable is going. But from here, let's go ahead and sum forces in the X direction. Or I could do forces in the Y. I'm down to only one unknown in each. Summing forces in the X direction. I have AX goes to the right. And the only other thing that I have is the X component of TB. So minus 1413 cosine 22 gets us to 0, our X component of TB. Again, even though this is a really easy equation for us to solve, write the full equilibrium equation out. That sum of what am I summing up, everything in there, and then it equals 0, and then solve it. Don't skip to AX equals 1413. Take your time. Do these steps through this. It'll help you be better, more likely to get the correct answer, less likely to make errors, which is what we want from our engineers, not making errors. So do the small steps that help you be successful. But if I solve that for AX, I'm going to get that AX is, this one solves to be positive 1,311 newtons. When I get this as positive, what that's telling me is I assume the right direction in my free body diagram, so I should say to the right. Put an arrow in there. That way we are getting magnitude and direction out from that. Finally, I can sum forces in the Y. Summing my forces in the Y direction. I have AY going up I have a y component of TB going up, plus TB is 14, 13. I want the y component, so sine 22, and then minus 850. Minus 850 gets us to 0. AY is the only unknown in this equation. I can solve for AY. I should get AY is a positive 321 newtons. Because this solves to be positive, it means I guessed the right direction here. It is going up, just like we assumed. So we'll report our answer as a positive with the correct direction on it. Again, rigid body equilibrium is going to keep showing up over and over and over. This is, in a nutshell, what a lot of people would say statics boils down to. Summing forces in the x, y, and moments. If we can't do that, we really don't know statics, is what I would say. So struggle through this. Get there. It's a challenge for everyone as we start that out. Let's get you there, though. If this was useful, stick around, hit that like and subscribe. Watch more videos. Let's get you an A with JJ.